Okay. So the plan for today is to do is to talk about more examples of dynamic programming. But of course, the best way to learn how to do it is to basically just code them up. So hopefully homework 3, I think, has this coding example, which doesn't look like it's a dynamic programming problem, but if you think about it a bit, you'll see that there's a dynamic program, there's a recurrence, overlapping subproblems, and you set up a table. And then the homework 4 gives you more exercises to do. And I think once you do a few of the exercises, you start seeing the pattern in dynamic programming. I wanted to take this example of constructing optimal binary search trees because, again, it's a classic dynamic programming problem. So let me just go over the problem again. And so the idea is, suppose there's a universe, and I should probably say ordered universe. So there's some ordered universe, let's say 1 to n, and you need to search for these elements. So just to give an example, you can assume that there's some object associated with each of those, and you'll have to fetch the object whenever this element or this key appears. Okay, so for example, one could be users of a website, and this is some object storing the user data, and so 1 to n, that denotes the user ID or whatever, some login ID. And so the obvious thing is you'll say, well, just you can have a binary search tree on these keys, and you might say, why not a hash table? And there's always a debate on whether to use a hash table or a search tree, but often hash tables require more memory because you have to allocate more memory, and sometimes that gets messy, that in many cases it's easier just to have a balanced binary search tree. So interestingly, I think the map in C++, even though it looks like it's a map, it's just a hash table, it's stored, I think they use a red black tree to actually implement it. Okay, so if you have this binary search tree and then you have multiple lookups, then you can say the running time is m log n. So m is the number of lookups, n is the size of the universe. This is sort of a standard fact with a balanced binary search tree. Now, what happens in practice is, this is what you will typically learn is, you just build a binary search tree, a balanced binary search tree, and that's it, is that some keys are more frequent than others. And so can you improve the lookup time given that fact? So again, just to take this example of users of a website, some users will log in more frequently than others. And you already know that beforehand using, let's say, historical data. So you look over the frequencies, you can see which users log in more frequently. And so you would like to have a search tree that would be faster for those users. So to make it concrete, we'll say, suppose there is a frequency function. And so this says that for every character, and I changed it from sigma to gamma because sigma looks like the summation sign. But the point is there's some universe of symbols, and for every symbol, the frequency f of that symbol is the number of lookups. It's the number of times that you're going to search for that element. And so in a binary search tree, every key or every character has a depth, right? And so we said, what is the total lookup or search time? So what we're doing is we're summing over all. Okay, so again, I changed the universe or the alphabet to gamma, just so that it doesn't look like sigma being a subscript of sigma. So for every gamma and gamma, you're going to multiply the frequency by the depth, right? Because the frequency is the number of times you search, and the depth is the amount of time that it takes to search for that element. And you're summing this over the entire universe. This is the total time. Okay? So the aim is to find the binary search tree that minimizes this lookup time. So it's important to distinguish that the f is like an input to your function, and the d is what you need to figure out. D is what your algorithm is computing. So I'll just state this out over here. F of gamma to n is the input, and you can just think of this input as like an array. It's just an ordered universe, and I'm just telling you the frequency for each. And the BST is the output, and the BST also implicitly gives you this function, right? Once you build a binary search tree, then you have a depth function for all the characters. Make sense? So you have to compute this binary search tree. Okay? Let me just give an example that maybe makes this a little more concrete. So I'm going to take a simple example of this universe just being the set of all characters, A, B, C, D, all the way to Z. Right? This is a simple ordered universe. The size of the universe is just 26. Right? And so why would you want to build a search tree on this size? So imagine you're doing some kind of, so as an example, suppose we're doing compression of a text. Now we'll see such examples with things like Huffman coding. So normally, if you store a character, right, how many bits does it take? Just normal representation. You have ASCII representation, right? It's 8 bits, right? So for each character, usually you have 8 bits. Right? And that's how you'll represent your text. Now what you might imagine is that actually some characters are more frequent than others. So you should use a shorter representation for those characters and a longer representation for other characters. Right? So for example, E or A, S, T, these are letters that are more frequent. And so frequent letters you might want to represent with like 2 bits or 3 bits. And it's okay to represent Z with like maybe 10 bits. And if you do this properly, you can actually compress your text significantly. This is like one of the most simplest methods of compression. And more fancier methods are basically, they're doing some form of this. Except instead of doing individual characters, they might look at blocks of characters. Okay? So you're doing compression of a text. So there is some mapping from your universe to bit strings. And this is sort of the compression. The compressed representation. So let's ignore about how you find this mapping. So there's some method that actually finds this mapping based on various calculations. Right? So now how do you actually do the compression of a new text? So you see this text, every time you see a character, you have to find out what is the compressed representation and put that down. And that's how you do the compression. Does that make sense? Right? That's how you would do it. So you need to build some lookup that tells you this mapping quickly. And that would be a binary search tree, right? You could build a binary search tree. So what you do is build a binary search tree on gamma and store the compressed representation in the nodes of the tree. Right, so I could basically build some tree, and so let's just say suppose this character over here is S, then what I would store here is whatever bit string I'm using to represent S. Right? And that's how I'd represent this information, so that when I actually see the character S, I would go to S and then I can fetch that. Right? This is sort of a very simple, this is a simple example of a data structure that you could build, and is a pretty efficient one for this process. Does this make sense? Now the question is, what binary search tree should you build? So you could say just build a normal balanced binary search tree. So what would your balanced binary search tree? So let's just do a balanced BST. The middle of this is something like M, right? So that would be like about maybe the 13th character. So you put the 12th or the 13th character over there, so you'd put M over here, right? And then you'd maybe look at the 6th or 7th character, maybe you'll put F over here, and then N, O, P, Q, R, S, maybe you put S over here, and then you keep building this tree, so on and so forth. And if you do this in the end, you'll get sort of like some kind of balanced tree. Does this make sense? So what is the problem with this is that maybe your letter E is down here. And E is about at the same depth as, I don't know, maybe something like W. But obviously E is going to be more frequently looked up than F, or maybe even S. Certainly more frequent than M. But your search time for M is much more quicker. Because if you're looking up for the bit string for M, you'll immediately get it with one operation. With E, you have to go all the way down. Does this make sense? Because E is more frequent. So what seems to be the better thing to do is to actually put E near the top. But now what's the problem? It's not going to be balanced. So there's some price that you pay for putting E at the top. And the price that you pay is that your tree, this part is going to be short, but this part is going to be much longer here. Right? Yeah? Because look at, it's a binary search tree, right? So E is not the middle of this universe. Yeah?
So the one on the left is just, if it's a higher letter than M, you go to the left. If it's lower than M, you go to the right.
Exactly.
But then on the right, couldn't you just mark it by frequency? It's like if there's more frequent than E. If there's more occurrences of than E, then go right. If there's less, then go left.
So, okay, so I'll answer that question in just a moment. Yeah.
Kind of tagging on to that question, yes, but why can't we put the alphabet afterward?
But then how do you search? So you're now processing this piece of text. You get the next character. How do you go and fetch where the representation is? So now to answer your question, you're saying you're going to use something else as the key, which is you're going to use the frequency. Now, you could, but that still doesn't solve this problem, right? So then what is your solution?
Yeah, I guess thinking about it further, if everything more frequently than E, well, E is the most frequent.
E is the most frequent element.
Yeah, so,
Everything is going to be less frequent than E. I mean, this is almost like a greedy solution. It's like put the most frequent thing at the top. I'm not saying it's the right one. But you see that there's a problem with that, which is now there are certain other characters that are going to, like, so this is not balanced anymore. So you have to pay, so you're paying the cost somewhere. Yeah?
You could sort of find some sort of remapping from your character universe based, if you sort it by descending frequency and basically somehow remap it to a different universe of 26, but E, which is the most frequent, has to fall in the middle.
Yeah, so yes, there is a way of doing that, which is you could do some sort of weighting by frequency and try to split the weights, which actually is a potential solution. But what I'll show you is that actually you can get the exact best. I'm going to go one step further than that. But yes, you could. There are ways of doing that. That's a valid way of doing things, because what you're saying is somehow. It's not like you want to split the universe, but you want to split the number of searches in half. So, but you see that what happens here is maybe because you did this, something like S and T are going to be down here, which is not the best thing because you want S&T also to be near the top. So there's some trade-off here. The trade-off is that if you just ignore all the frequencies altogether, then you get this perfect balance, which seems to be good for most things, but is bad for the few things that might be frequent. How do you find the exact best tree if I tell you what the frequencies are? That's really what this problem is about, yeah?
Could you have we already established you can't do frequency, lower frequency and greater frequency. Could you have a table that encodes the path to each of them and just arbitrarily create it so that it's even? So you could have the second most frequent be the left, third most frequent be to the right, but then you have a table saying, oh, well, S is the most, third most frequent, that means to go to the right of B. You could map it as an order of tree traversals instead of just having it.
The lookup then becomes a little more complicated, right? Like the good thing about a binary search tree is that the lookup then becomes really quick. Like this is optimized lookup. And especially if you think of like processing a large piece of text, you want every character lookup to be like some simple operation. If that involves building a table and looking through the table, it might be that the overhead of doing that is much more than just doing a search tree. Like the number of operations. Because here like we're counting exactly how many operations we're doing. You could reorganize the alphabet, but then you have to figure out how to reorganize it. No, but then frequency doesn't give you a way of, you want an ordering. It doesn't make sense to sort the frequencies and take that ordering, because that doesn't particularly buy you anything. Right? What you want is for more frequent characters to be near the top and less frequent to be at the bottom. Yeah? Okay, so this is a prefix-free encoding, yes. You are trying to come up with the optimal prefix-free encoding, which is, okay, go on, yeah. I'm saying build a tree with that somehow.
Yeah.
How do you know that's the best tree? It's not obvious. Right? Maybe there is some choice that you could do before, which is less optimal, but it helps you later on. Does that make sense? Like, because the problem is, even though E is the most frequent, by doing this, S and T end up down here. And maybe instead of doing this, like maybe what you should have done is taken F over here, but put E down there. And that way the S and T would move up, but the E would also move up. So there are all these like little choices that need to be made. I mean, the reason for this discussion is I hope I've convinced you this problem is not obvious. There are lots of ideas you can throw at it. And all these ideas are pretty reasonable things to do. Right? So what I'm going to show you is if you think about it with dynamic programming, then you don't even need to worry about these ideas. I can guarantee that you'll get the optimal solution over any possible tree. Yeah?
Do we need a table for dynamic programming?
Yeah, we're going to build a table. Yeah.
But then it's overhead again, no?
No, I'm not building a table to do the actual lookup. I'm building a table to figure out what the best tree is, and then I just build that tree.
Okay.
So I'm not doing dynamic programming for the lookup. I'm still building the best binary search tree with the table. So the table is like a pre-processing step that I'll do to build this binary search tree, and then I have the best binary search tree for that frequency. Does that answer your question? Okay. Yeah?
What if, okay, so I think I'm getting ahead of myself, but what if the frequencies keep updating?
That's a good question. So the frequencies keep changing, then of course this approach overall wouldn't make that much sense. So what usually you have is that, especially for something like the English alphabet, you usually have historic frequency. And you just use that historical frequency. If you're using like login data, then you just use historical frequency. Now, if that keeps changing rapidly, then this isn't a good idea. So, but that's a valid point. Like then people do ask, like suppose that changed, can you then quickly update the tree? And now we're going into research topics. But yeah, that's a valid question. Okay, makes sense? So hopefully I've justified the problem. We haven't gone into dynamic programming yet. So the problem again is just minimizing this. Regardless of how you think about this problem, you would all agree that your approach is really to minimize this quantity. And again, so this is, maybe stepping back, I'll reiterate that one thing that dynamic programming does is it's like a tool that you should use. That sometimes instead of having to think hard about a problem and figuring out what exactly is going on, it sort of just gives you the solution using this technique. Right? Instead of, you can think, okay, maybe I should put the most frequent over here, I should cut by frequency, or do this or do that. But if you write down the recurrence and you notice a dynamic program, then you don't even have to worry about all of that, because the code will do it for you. Okay? Okay. So good. So let's, again, for concreteness, I'm just going to use this as the universe. Just so that, I think we agree with this example and this sort of keeps things easy. Okay, so when building a binary search tree, what is the first choice? So I'm asking this question because really I'm just asking, can we solve the optimal BST problem using recursion? And if you think about it, trees are naturally like recursive objects. So if you're building a binary search tree, what is the first thing that you need to do? Yeah? You have to pick a root, right? And how many choices for the root do you have? You have 26 choices for the root. Okay. So the first choice is pick a root. And I'll refer to this root as gamma. So gamma is just some character from A to Z. Okay, so once you pick this, now what? You have to pick the children, but now you've already done a split. You've done a recursive split, right? Because what happens is you've broken this down. So if I'm just thinking of A to Z as yours, and you've chosen some character gamma here. Now the left side only deals with the left half, which I guess is not really a half, but the left portion, and the right side only deals with the right portion, right? And that's just building an optimal binary search tree for those frequencies, right? So what you have over here is some tree that deals with everything in this gamma, which I'll say, okay, I'm just writing this notation here. Hopefully that makes sense, because this is like the universe that's less than gamma. This is the universe that's more than gamma, right? So I've split the universe into two parts. And once I've split the universe into two parts, what do I need to do? I just need to figure out an optimal solution here. So I could just use recursion there. Yeah? Well, yeah, but I don't even want to think about that. I just want to do recursion. So I want to say, suppose there's a recursive procedure to solve this. I'm going to define the recursive procedure. So let me think of a recursive procedure opt BST. What does opt BST do? It basically takes a universe and it takes the frequencies for that universe and builds a tree. Right, so opt, so I'll say there's some universe that I call gamma, and then there's the associated frequency, right? So this is the universe. These are the frequencies. And so what this procedure is going to do is it could just try out every possible route, and then for every route, make recursive calls to figure out what the left and right tree look like. Yeah?
Sorry, I think I might have missed it. Is the frequency for each element?
Yeah. Yeah. Yeah, that's, this is what we started with, right? I mean, okay, so the frequency is the number of times you're going to look that element up. Right? So for example, for E, the frequency is going to be large. For maybe Z, it's going to be small, whatever. So just think of these are just like two arrays. Yeah? Does it make sense? So let me just write it down sort of in English, and then we can write the recurrence based on that, right? So what we'll do is, for every possible root gamma, we get two recursive subproblems. Okay, so we're going to have to write this a little carefully. So what I'll say is, what are the recursive subproblems? You get opt BST. You get all the characters that are less than gamma. And I'll just say you take all the frequencies of the characters less than gamma, the corresponding frequencies. Right? Because you can think of your frequency vector as some frequency vector that's also ordered by gamma. Yeah? Sorry, can you just?
Does the frequency vector matter on how
You could just use you can just keep the old one, you mean? Yeah, you could just keep the full frequency vector because you're only looking at these. So okay, so maybe fair enough. I'll get rid of that substrate. Let's keep it even simpler. So yeah, so you have this frequency thing, although it has frequencies of elements that are outside that, but you don't care. Okay, good. And then you have opt BST greater than gamma, again with the same frequencies. So at this point, you're right. Actually, the frequencies are not that relevant because now they're the same for every recursive call. It's just the same set of frequencies, right? So I can even drop the frequency entirely in my discussion. Assume that it's just fixed. It's some global variable that I've fixed. So this opt BST, which is making a call on the entire universe, now makes a call on two sub-universes. I have to do this for every possible route. Okay? But then if I do this for every possible route, then for every possible route, I also need to figure out now what is my total lookup cost for this. Now this requires a little bit of thought, so I'm going to do this a little carefully. Okay, does this make sense? Okay. Okay, so now let's see if I can. I'll put this all side by side so that you can see it. Okay, so I'll say, let's say the total lookup or the search time in, okay, so maybe let me draw it this way. So here's gamma. Now let's say you do this recursive call for that choice of gamma. You're going to get some tree here, which I call t less than gamma, and you're going to get some other tree here, which is t greater than gamma, based on the recursive call. So recursion basically outputs something, you get t less than gamma, t greater than gamma. Now this is going to have some search time. So I'll say the total lookup search time in t less than gamma is, I'll just call, I'll give it some name. So that is S, again, less than gamma. That's just like the total search time for this frequency in this tree. Make sense? That's just saying that if you searched in this tree, okay, that is the total lookup time for all of these characters. Yeah? For all the less than gamma characters. Is the total lookup time over all the frequency in that tree. But this tree is only a portion of the actual big tree. So here's my question. Like, refer to this entire tree as tree. What is the total lookup time of characters in the same portion in T? So what I gave you here is that the total lookup time is just in this left part. But your actual tree is the big one. So I'm going to give you some options and then hopefully this will make some sense here. Is it S less than gamma plus the summation over, okay, so let me, if this notation is confusing, just let me know. Is it that? I'll write down these formulas and then I'll parse them. Or is it? Okay, so what am I saying here? This is the total lookup time in the small tree for all these characters. Now, because it's part of a bigger tree, the search time is going to be different. So that second summation says, what is the difference? I'm summing over all the characters gamma prime less than gamma, because those are the only things I care about. Right? I'm asking, what is the extra cost that you're paying? Because you're now part of a bigger tree. This question makes sense? I'll give you a few minutes to look at these formulas and look at them carefully. You can talk amongst yourselves or whatever if you want. You have a question? D is the, yeah, thanks. D is the depth of gamma in this tree. In that tree. D is the depth in that tree. Right, so this is D is the depth in the tree. Think a little carefully. I'll give you a minute or two to ponder. Question?
Should that be is S less than gamma?
Sorry?
For the total search, should that be is?
This?
No, yeah. So the total lookup / search time in tree sub less than gamma is not in.
Thank you. Yeah, is. Yeah, is. Excuse me. Yeah, okay, so what's the answer? Okay, it's all over the place. Very good. Okay, so then I won't tell you the answer. Let me explain what's going on, and then I think you'll see. Okay, so let's just say that there was some character, gamma prime, whose depth is d gamma prime, right? What is its depth in that smaller tree, t less than gamma prime? Yeah? Minus, right? 1 minus. It's like whatever the depth is, minus 1. Or rather, the depth in the small tree is 1 less the depth in the bigger tree. Now, what this tells you is essentially like the sum of depths weighted by frequency in the smaller tree. What you want is the weighted sum of depths in the larger tree. Yeah? And in the larger tree, the depths have just gone up by 1. They've all gone up by 1 for all these characters. It's exactly gone up by 1. Now I will let you, I don't know if that helps. Yeah?
Can you re-explain the depths go up by 1 in the larger?
So let's just say you have some character that's down here. This has some depth d. What is its depth in the bigger tree? It's d plus 1. That's all I'm saying. Yeah?
I'm not really sure. So you have gamma prime is less than gamma. But wouldn't it be greater than? Wouldn't gamma prime be greater than gamma? Because we already considered like.
No, I'm okay. So here's what I'm trying to do, right? Should it be n?
In, like, gamma prime in gamma for this summation?
Okay, so hang on. Okay, now we're wrapping ourselves up in notation. Let's step back a bit, right? What am I saying? Okay, let's go back. We chose a root. We split the universe into 2 parts. We made a recursive call for each of them to get the optimal tree. Now, what we're trying to figure out is that given the optimal trees, and given that probably the recursive procedure also told us the total search cost for that tree, what is the total search cost for the bigger tree? Right? Because that's the way that we're going to set up any kind of recursion. Like when you make these recursive choices, how do you know which is the best? Yeah, question? Okay, all right, hang on. If you have the answer, then hang on. Okay, so far so good? So what am I trying to do now? I'm saying, look, suppose the total lookup cost in that smaller tree for all the characters in that smaller tree is s less than gamma. This is just and assuming that recursion will sort of tell us what that is. Once you have that number, you want to figure out what it's going to be for the bigger tree, and then you also have to do it for the other side. Sum all of this stuff up, you get the estimate for the larger tree, and then you minimize that over all gamma. Yeah?
We're basically trying to do the optimality principle, right? Like you're trying to show that it's optimal in the other one, and then in total it's also optimal.
I'm not even going that far. I'm doing something much simpler here. Okay. What am I trying to do? Okay, so let's just say you want to use recursion here. So you're going to get these solutions. And then what? How do you know which is the best route to choose? Yeah? Frequencies are fixed. Frequencies are fixed. So you chose this route and you got these trees. So you have these 26 possible choices. And you got the recursive solution for each part. But how do you know which is the best? And I told you the solution for each recursive part as well. Does this question make sense? You have to figure out what is going to be the total search cost for the bigger tree. The smaller tree is fine, you have the recursive solution. So from that solution or from that search cost, you have to figure out what it's going to be for the whole thing. Question? No. No.
What?
You have a question? No. No, okay. All right. I thought you did because you looked at me with a puzzled face. But that might just be that everyone's puzzled. So fair enough. Okay, good. So I'm just saying the total search time in the smaller tree is this quantity, which let's say you got by recursion. How are you going to figure out what is the total lookup time of all of the characters in that tree in the bigger tree? And I told you that the depth has gone up by 1. Okay, so now I pose my question again. Okay, what is the answer? Yeah? It's blue. It's blue. Why?
Because, effectively the formula is like F, not 1, but because we're doing D plus 1.
You're doing D plus 1.
And the summation of one part
Would be the
call plus the F times.
Plus the F time. So I'll spell this out. So what does this mean? It's just saying, look at the search cost for each of these. For each character, it's gone up by 1. How many characters were there totally? It's a sum of frequencies. So it just went up by 1. It doesn't go up by the depth. Because no matter how deep it is, it's still just going up by 1. So if the total frequency of that was 1,000, then you're going to pay 1,000 more operations. It doesn't matter what the depths are. Yeah? So far so good? Yep? Yeah.
So this is saying the total lookup time for every character to the left of gamma is going to be a factor of the frequency.
Additive. You're adding the frequency.
Okay.
You're adding the total frequency. You're not, yeah?
So basically, the less frequent it is, this is going to cost more. Or no, this is just the sum of the.
This is just the sum. It's just like saying that I did recursion, I got some solution, and I need to figure out what it's going to be in the whole thing.
So we would have to optimize S less than gamma.
Let's get there. Yeah. I mean, again, I'm thinking recursion. So I'm assuming that just somehow I figured this out by just a recursive call. Okay? Yeah, so far so good? Sort of, kind of. Yeah, question.
Not, but now that how do you come up with the recurrence relation?
Yeah, exactly, right? So all of this is how do I come up with the recurrence eventually, right?
Is it just observation and practice?
Oh, you mean how did I come up with all of this? Well, I looked at the book, but anyway. It's a lot of practice. But honestly, I mean, again, like the way is... okay, so like if you do the homeworks, right? If you do homework, I don't know if has any of you seen homework 3? Yeah, sort of, kind of. It's the way it's phrased is not obviously dynamic programming. I think if you paid attention to it. Does any of you do you have any guesses what? There's a theorem, a deep theorem of math that it relates to. Yeah?
It's like the square root of the number, it's like the maximum of the square, also the number.
Okay, so not entirely. So if you solve it, right, I think you'll have an aha moment when you actually look at the solutions. You'll be quite surprised. So the point is, how do you figure out that basically you use dynamic programming there? Is you kind of go through this process of recursion. That's always the first place to start. Think of a recursive solution. Now, once you think of a recursive solution, you'll be on the right path. So that's why I'm trying to phrase this as saying, how do you figure out all of this stuff? You say, well, suppose I did recursion. I've solved these sub-problems. How do I know which is my best choice? That is what is going to give me the recurrence. That make sense? Huh? That's usually the hard part. But once you think, like it's like recursion, right? I mean, I'm sure that each of you, or at least most of you, struggled with recursion the first time you did it, right? It takes a long time to kind of get it. But once you get it, then it becomes this problem-solving tool. And it's the same thing with dynamic programming. Like once you recognize this pattern, that it's about building a recurrence using recursion, you'll see the pattern. Let's take a break for a couple minutes, okay? And then when we come back, we'll solve this problem. Okay, let's continue. So, I don't know, I feel that maybe this is getting more confusing than it needs to be. But does this make sense? I mean, like, that basically you're trying to find out what the root is. You have a recursive procedure that solves these. But given these, you have to figure out what is the cost of the overall thing so that you can minimize your overall possible roots. So, I'm going to go ahead and write down this expression and then maybe things will start making more sense. So I said the total lookup time of all the characters in the left part is basically whatever is the optimal solution there plus the sum of frequencies of the left part. Similarly, the total search time or the lookup time of characters in this, in the bigger tree, is S greater than gamma. It's all the stuff that's more, plus the sum of all those frequencies, right? Just analogously. What is the total search time for the root character gamma? Right? So that's the root that you chose. Is it just 1? Is it f of gamma? Or is it d of gamma? What is the total search time for all the characters? The total search time for the root character. Like by total, I mean total over all the searches you're going to make, and you know how many searches you're going to make. That's given by the frequency. Right? Question? So you're looking at all the characters in this tree. So those are all the characters that are greater, that's gamma prime is summing over everything in that tree. Right? Gamma prime greater than gamma, f of gamma prime. Yeah?
This part just represents the number of times it will be accessed, and the distance is just 1.
The distance is just 1, right? So it's the same argument as before. It's just saying that you look at the total search times in these trees, and you're basically just adding 1 to all of them. Okay? Now, what is the total search time for the root character? Yeah? Question?
Is this searching over the universe to find the most optimal root, or is this trying to just find something?
You fixed the root. Like, this is what the tree looks like. I'm just saying you're looking at that character. How much time are you going to spend looking for that character, total? Yeah, right. It's f of gamma, right? It's 1 for each search, but you do f of gamma searches. Yeah? So now that you have all these pieces, you can put them together to figure out what is the total search time in this tree. So now I'll write this down. So I'll say the total search time in this tree is S less than gamma, which is whatever the recursive solution was on that part, plus the summation of gamma prime less than gamma of f of gamma prime, plus S greater than gamma, summation of gamma prime greater than gamma of f of gamma prime, plus f of gamma. Right? This is what the total search time is going to be for that bigger tree. Make sense? And so you can see that all of these things, they just sum up to be the total sum of frequencies. Right? So all of that, yes?
Why is there a prime for the first two but not the last?
So gamma prime is the summand, right? I'm summing over gamma prime, right? It's like the variable of the sum, right? So what I get is I get S less than gamma plus S greater than gamma plus just the sum over all characters, I'll just say over all gamma prime in this universe of f of gamma prime. This is just the sum of frequencies. So these you got by recursive calls. Okay? Yeah.
Okay, dumb question. Maybe I just don't understand like the algorithm for what we're trying to do here. But why do you have to sum over the frequencies of gamma prime?
So what you're trying to do is so by recursion, so what does recursion tell you? Recursion says give me some frequencies for some set of characters, I'll give you the best tree. You got the best tree for the left part and the right part. And now you're trying to figure out what is going to be the total cost on the whole tree. And so that's why we went through this process over here.
But why would the frequency affect like the runtime?
It doesn't affect, there's no run, well, because the search time is, so if you go back to the problem, this is where I think, remember we said what is the total lookup time for doing these many searches of this character? Because the frequency tells you how many times you're going to look something up. So it's important to separate two things. The formulation of the problem has these frequencies. The tree that you're building is basically figuring out what the depths should be.
So the frequency is like a table of how many A's, B's, C's, G's.
You are going to see, exactly.
And we have to figure out like, D.
Yes. Which is what I said here, right? F is the input, the BST is the output. Yeah? Okay. So, does this sort of make sense? So now let me write it out a little bit more formally. So suppose opt BST, okay, now so I'll write this out in this way just to simplify things, and then maybe. So here's your universe gamma. Okay? I take any two characters in this. Now, just because maybe Greek symbols are throwing you off, I'm going to move to English. Okay? I'm just going to use I and J to index the symbols. It's like you're looking at the ith character in this list and the jth character in this list. And you're looking at this portion in between them. And you're saying, let me look at the total search cost for just this part. What is the optimal search cost going to be? Does this make sense? Like, because if you notice, you're basically looking at intervals of characters. So I'm going to write this down. Outputs. The optimal search time over all BSTs over gamma of I to gamma of j, to this portion, over the universe, over that universe. Does that make sense? Suppose you build a recursive procedure. I'm going to write the recurrence for you. I'm going to say opt BST ij is equal to the minimum over all k in between I and j. So all k in between of opt BST I to k minus 1 plus opt BST of k plus 1 to j plus the sum over all k going from I to j of the frequency of that of the kth character, right? So the frequencies are here, say. This is the recurrence. Yeah?
I still don't get why that's a mean of the frequencies. Because, well, what basically I would say is that the amount of times that we have to do for a charter times the optimal best path of the chart.
Yeah, but you have to combine all of these paths into one tree. You can't independently choose a different path for each, right? The point is you have to get one tree that gives you all the paths. And so there are dependencies amongst these different depths.
But still, why summation?
Sorry?
Still, I don't get why summation of the frequencies.
So that was the previous argument over here.
Yeah, but still.
Okay, so let's move on and then, we'll come back to this point. But assuming that you understand this, do you see why this is the recurrence? It's saying that look at every possible root in the middle, right? You made a recursive call to the left part, that gives you this, recursive to the right part, plus this additional sum, which is what we got from this argument here. And then you minimize this over all possible roots in the middle. Right? So this is like all possible roots. Does this make sense? Yes, no, this is a good time to. I'm going to make a homework out of this. I think this is the only way that this is going to become completely clear. You write the code for this and then everything will be clear. Okay, next homework. Homework 5 is decided now. Okay? Someone was saying homework 3 was too easy. So let's do this now.
I think we got it now. I think it's okay. I think we got it.
Huh?
Everyone understands it here, so I think we're good, yeah.
Oh, you don't need to do this as well. Well, then it's even better, right? Then homework 5 is easy for you. Win-win. Either it's easy for you or I teach you something. So either case, somebody wins. Okay. So what is this saying? It's just saying the optimal binary search tree in this range is given by the optimal binary search tree in that range, the total cost of that, and the total cost of this, plus the sum of all frequencies. You minimize this over all possible roots in between. This is the recurrence. Now you have this recurrence, so you can build up you can ignore how you got this recurrence. Once you have this recurrence, the dynamic program is now obvious. Yeah?
So you start in the middle, and you choose that root, and then you try to construct the tree, and that's where the summation of frequencies comes from.
I'm sorry, say that again?
Sorry. So opt BST, it chooses a root from K, right?
From some range, yeah.
Okay. And then it constructs its own tree, and that's where the summation of the frequencies comes from.
So the summation of frequencies comes up because once you get the optimal cost of this tree, or the search time, that is only the search time for that range, for that tree. But when you stitch it together to make this bigger tree, you have to account for the fact that the search time here is now increased by 1 for each of them. And so that's why you sort of add that quantity. Yeah? And so this minimum gives you the optimal binary search tree time, basically. It actually doesn't tell you the tree exactly. It only tells you the time. And now you're going to ask, how do you figure out the tree? That's exactly why I give you homework. It's the same, remember, like we did this in all these dynamic programs. You build 2 tables, right? One table for the cost, another one for the choices, And once you keep track of the choices, you can build the tree. Yeah.
Look at them. I'm not sure this is a valid question, but in this whole minimum of all k's between I to j, no matter if you have multiple k's, that summation of k.
Yeah. Good observation. Yeah.
That'll always be the same.
That's the same. Good observation. This is the same. It doesn't matter. It actually doesn't affect anything. But the reason you put it in there is so that you have the right quantity, because as you build the dynamic program, you want the right answer in the end. But you're right that the choice doesn't depend on it. Like the argument of the minimum does not depend on it, but the minimum will depend on it. Yeah, exactly. Okay? So, okay, now we have all of this. If the universe has size n, how many possible arguments as tuples, right? You're looking at the entire argument. Does op BST ij have? Is it theta of n, theta of n squared, theta of n cubed? How many possible arguments are there? Okay, so you see it's theta of n squared because there are n choices for one, n choices for the other. It's actually n choose 2, it's even smaller by half. Okay, and so now we can build our dynamic programming table. So okay, question? No. All right. So I'm just going to put I over here and j over here. And I is going to go from 0 to n minus 1, right? Because this was our universe. And so you have one index I. You have another index j. I'm just going to sort j in the opposite direction, n minus 1 to 0, just so that this is the entry that I'm really looking for. I always like to look for that top left entry as the solution. Okay? And you only care about the case where I is less than j, right? Because it's an interval. So let me make sure I'm doing this right. And so it's going to look like that, right? So you only, there's nothing over here. It's only in this part. Because for I is equal to 0, j will go from n minus 1 to 0. For I is equal to 1, j goes from n minus 1 to 1. For I is equal to n minus 1, there's only one entry here. Right? So this is the portion of the table that we need to fill in. Does that make sense? You don't need to fill in this bottom part because okay. So what is the base case? When I is equal to j. So when I is equal to j, what is this value? Yeah? It's just f of I, right? You have one element. What is the optimal binary search tree for one element? It's just that element. What is the search time? It's the number of times you have to look that thing up. Total search time. It's just going to be f of I. Yeah, so far so good? So how do you fill up the table now? So let me just write down the procedure to fill up the table, and then based on that we can come up with the output. So you can see pretty clearly from here that once you have these entries, you can get this entry in how much time? Worst case. What is the length of that loop, yeah?
And the summation.
It's just Yeah, it's n because you're only looping over one thing. Like this is some fixed number. And this was observed earlier, right? This is a fixed number. So you compute this, and then you just loop over all the things in between. So for each entry of the table, you need to do one loop. And there are n squared entries in the table, and so it'll be n cubed. Okay? Okay, so let me write down the procedure that actually fills this table, and then we'll just sort of go back and look over the whole thing so we understand this. Okay, does this make sense? So, again, a lot of the hard work went into figuring this part out. That's where we had to like draw the tree and build all those things. But if you kind of believe that, then the recurrence, once you have this recurrence, which is I guess what you were asking, like how do you get this recurrence? Yeah, okay, so that was the hard part. But once you get the recurrence, the rest of it is a pretty much standard recipe to follow. Right? You look at how many possible arguments are there, and we discussed there is only n square possible arguments. Once you have n square possible arguments, that gives you a table. So now you have this table over here, and then once you have this table, you can basically, you just figure out what the base case of this table is, which is the base case of the recursion, which is when your alphabet, the universe size is 1. There's just one character to look for. You just build a very simple tree, which is a single node. The total search time for that is just its frequency. Okay? So far so good. And then let me just write down the procedure to fill up the table. Actually, I forgot to put page numbers, which maybe I should just go ahead and do right now before I forget. Okay, 41, 42, no, 43. Nah, I messed up. Forget it. To fill up the table. So I'll just say the first step is for all I in 0 to n minus 1. I'll write this out as a table, op BST of I, comma I is just f of I. And then now we just need to do this in the right order, so we have to be a little careful here. So if you really think about it, the way that you fill up this table is not row by row or column by column. So what is it? What is the procedure to fill up the table? And let me again show this to you. So this is the recurrence. How should you fill up the table? Diagonals. So you go diagonal by diagonal. Right? So you fill up this diagonal, then that diagonal, then that diagonal. Because the diagonal is telling you the size of the universe. Right? The j minus I is telling you the size of the universe. So you fill it up in order of the size. So you fill up this diagonal first, then that diagonal, then that diagonal, so on and so forth, all the way to the top. Which is one of the reasons to do this dynamic programming exercise, is that it's sort of different from the other ones. When the other ones, the table filling is a little more straightforward. Here it's a little more, it's different. Okay? All right? So I'll just write this out. I'll just say for the size, because really you're looking at the size of the universe. The size will go from 1 to n minus 1. So I'm going to be a little careless with the indices here, because I don't want to I don't want to focus too much on exactly like how I set up the index, but rather just understand how the table works. So for this size, I'll say for I going, how should I do this? Yeah, I'll do this. Okay. 0 to n minus 1. Now I can set up the table over here. So I'll set j is equal to I plus the size. And then say opt BST I j is equal to then this min. Okay, so I'm writing this out in mathematical notation because I haven't written, I'm not adding another for loop there, but this is going to be using a for loop. So the min over all k in this interval, the min of all k in this interval of opt BST I k minus 1 plus opt BST of k plus 1 j plus this summation over all f of, okay, so this is overloading indices with f of L is going from I to j. Does this make sense? So this is exactly the recurrence before. This is like an O of n to compute because you're doing a min over all of these. And so you have these nested for loops, and so your total is O of n cubed. Okay? And then there's a more clever way of filling up the table, and you can actually get O of n squared to solve this problem. But the table size is still n squared. Okay? So this is, yeah, go on. This is the iterative, this is the table.
Yeah, and if you were to just write a recursive solution directly, you would have a base case and a recurrence relation to solve the problem. For the iterative, like you said, is the right one, and yeah, that's it.
Yeah, does it make sense? Question? Is this, yeah?
How do we find the best case then? Like, this is just the optimal time for it, but how do we build the tree from this?
Okay, so how do you actually build the tree from it? Okay, actually, how do you build the tree from it? Anyone? Yeah? Okay, backtrack how? Yeah?
So you have the best route for the entire tree. Then based off of
How do you get that?
the top left from the table.
No, the table just tells you the value. These tables are only giving you values. It's going back to the question that someone had. Yeah?
You find the minimum. Well, no, wait.
Yeah?
Do you construct it along the way?
How?
Memorization.
Yeah?
You could store the one you select, and I think that's enough information that you can reconstruct it.
Yeah. So when you find the minimum here, you store the argument, you store which was the k.
So with every, like the for loop is there, that is not right. So in that case, as soon as we find a minimum, we store that particular.
You store the value, but you also store who gave you the minimum. And that is the root for ij. And as long as you know the root for every interval, you can always just reconstruct the tree. Yeah?
So the root that you choose to be the minimum, that necessarily informs the structure of the tree.
It just tells you the root.
Okay.
But then once you know the root for every possible tree, then you can get it, right? Because you, right? Okay, maybe I should write this, yeah.
So suppose in a list of, we are ordering in such a way, we're building that and stores the roots. So for example, any I, that is the root, so the left part would be the left subtree and the right part would be
Right subtree. And then you just go and look up what the root is going to be for that. So, okay, maybe I'll just write this over here. What you can do is, maybe I'll just write this over here, almost as a step 3. I'll just say that I can create this root ij is going to be the k that minimized the above quantity. Right? You get the min from there. So now when you're finally done, if you look at the root table, the root sort of array, there's nothing here. What you get over here will be the root for the overall tree. So maybe that root is, I don't know, like I called it gamma, right? So you found out what gamma is. Then what is the root over here? So you basically look up what is the root of 0 gamma minus 1. And then over here you look up the root of gamma plus 1 n. And then you'll get something over here and something over here and so on and so forth, and you can build the tree. Yeah?
How do we know that the root process tree is balanced?
It's not balanced. It's optimal. In terms of the total search cost, it's optimal.
And okay, another question.
Mm-hmm.
But this is more about a recursive solution, and in that, like, how are we building that tree? Whenever we encounter, okay, we have to go recursive, we store that solution that we found.
Okay, yeah.
So like,
You're asking about the implementation of the recursive solution?
yeah, basically, as we do return to that recurrence relation, and we store that recurrence,
So, sorry, okay, I'll let you ask your question. Let me first say something. In general, you wouldn't want to implement this recursively.
but writing iteratively is, I think, much harder.
It's true. So there is, I think that the way you approach this is you write this recursive thing, but you don't think about actually solving the recurrence. But go on, now I'll let you ask your question, sorry.
No, I initially started doing it iteratively, but then I found it much harder.
Sure.
So then he was telling me to solve the problem because
Think about recursively, yes, yes.
then build the iterative.
Yeah, that's true. But then when you write the recurrence, you don't have to then figure out how to implement this recurrence as a recursive procedure.
Okay, we can skip the recursive step if you just know this.
But this gives you the recursive algorithm at some level. I should just write here is that in the recurrence then you have a base case, and the base case is just opt BST of I comma I is equal to fi, right? So then that gives you the base case. Yeah.
According to that formula, like when all the frequencies are added, summation of f of k, so the same thing will be repeated for of BST I to k minus 1, right? So yeah, inside that, so wouldn't it return in such a way that, let's suppose like E is the most frequent. So like let's suppose the count of E is like 10. So that 10 and the next largest frequency count is 8. So if that 10 is in the left or right subtree, then there will be 2 more counted in either of them. So like 10 as the root and then the...
Sure, I mean, yes, you are sort of expanding that count. If you uncoil the whole thing, then you're getting the full depth. You are getting the full depth, but you're breaking it up sort of level by level. Okay? Any questions? Darn, now I have to come up with an assignment. That's a lot of work for me.
You don't have to.
No, I think I have to. I think I do have to. But I was going to do something else. But anyway, yeah.
No, I was saying we get it now. We don't need to do
Yeah. So, sorry, this is maybe, the K is overloaded here. So let me just use a different variable here. Like this loop variable is different from that. That one. Oh, if I hits, yeah, if they're, then you just set it to be 0. Like you could imagine that essentially all of these are just 0. You mean if this is like I and I minus 1, you can just like say it's 0. Because there's like no universe in some sense. The universe is empty. Yeah. I guess technically I should have set the K going from I plus 1 to J minus 1. And then it would have been safer. Yeah. Okay? Yes? It's not that difficult, honestly. Like once you write it down, it's not going to be that difficult. It's going to be like maybe 20 lines of code. Okay? Once you write it down. But it's coming up with it, which is usually the coming up with the recurrence, which is the hard part. So I'm just going to sort of, there are a few minutes, so let me just sum everything that I've said so far, right? So the way to really look at this problem when you step back is really think about the formulation as given over here. To me, that is the clearest way to like formalize it. It says that I'm given a frequency. I need to find a tree so that this sort of sum, this weighted sum of depths is minimized. And the weight is given by the frequency. Right? So this gives you the total lookup or search time. And you need to find the tree that minimizes this total cost. It's not as if your algorithm is going to actually do all these searches. That's not the point, right? You're basically setting up this tree so that this will be minimized. So to do that, you start with this first observation that when you build a binary search tree, what is your first choice? It's the root. So you have to figure out what is the best route to choose for this tree. The way that you get the best route is now we're going to come up with a recursive procedure that's going to figure out this best route. And the recursive procedure, we say, well, recursively we know how to figure out the best tree for the left and the best tree for the right part. And if we know what is the total search time in each of those, we have to put it together to get a search time for the whole thing. And that gives us this sort of formula over here. Which is we're saying, look at the total sum of search times in the left part, and look at the total sum of the search times in the right part, and then you have to add the total frequency, and that was that whole argument that we did with the tree and adding the 1 and all that stuff. Right? But that argument is only needed to get there. So once you have that, you have this formula that tells you if by recursion you can find out what is the best search cost in the left part and the best of the right, you just add those together and you add the frequencies of all the elements in that universe that you're looking at. Right? And so when you step back and write this out, you get that the optimal binary search tree of an interval ij. So because I'm looking at the interval as like a subinterval of the universe, of this interval, I choose all possible routes in between. I look at the optimal binary search tree for the left, the optimal binary search tree for the right part, and then sum all the frequencies. And if I minimize this overall quantity over all possible routes, I get the best possible choice of a route. The base case is basically when the universe just has size 1, in which case you're just getting the frequency. Once you have this recurrence, then you can write out, you can write out the table, and the table in this case has size n squared. But to fill up each entry takes you O of n time, because there's a for loop to fill it up. And so you put this all together, this gives you the optimal binary search tree. And to actually get the root, you basically have to get that choice in between. And if you store the choice, you get the root, and then from there you can build the tree. Okay? Okay, so we have 1 minute left. I'm not going to start the next thing in 1 minute. So we'll end here. And I guess now I'm on the hook for homework 5.